Hey everybody, welcome back to my channel. My name is Calvin Lin, and this is part 3 in my unsupervised learning series. Last time we covered HDBscan, or density-based spatial clustering of applications. HDBscan is a machine learning algorithm that groups together nearby data points into clusters based on their density, while also identifying points that are not part of any cluster. Today, we'll be covering HDBscan, which is a variation of the HDBscan algorithm. HDBscan is essentially HDBscan's smarter cousin. HDBscan asks you to pick one global density threshold, the parameter EPS, and that only works if your data has uniform density. However, real data rarely does. HDBscan removes that guessing by building a full hierarchy of density-based clusterings and then selecting the clusters that are most stable across scales. Under the hood, it computes a core distance for each point, meaning how far you must go to find a dense neighborhood, inflates pairwise distances with mutual reachability, so sparse bridges look long and dense interiors look short, builds a minimum spanning tree of those adjusted distances, and then cuts that tree from coarse to fine to reveal a cluster hierarchy. From that hierarchy, it picks clusters by stability. Branches that persist across a wide range of densities survive, while points that never belong anywhere confidently are labeled as noise, or -1. You can control the granularity with two knobs, that being min cluster size, which is the smallest group you'll accept as a real cluster, and optionally you can also choose min samples, which makes your algorithm more conservative at the boundaries. A bonus you don't get with classic HDBscan is that membership strength per point, which is a number from 0 to 1 that tells you how confidently the algorithm believes a point belongs in its assigned cluster. We'll be working with the mall customers dataset as usual, from Kaggle. Our dataset has 5 columns: customer ID, genre, age, annual income, and spending score, which is a range from 1 to 100. For the purposes of our demonstration, we'll just stick with annual income and spending score. To start, I'm importing NumPy, Pandas, and Matplotlib. We'll also be importing our standard scaler. And finally, we'll be importing HDBscan. I've also created a helper function called scatter. This creates for us a scatter point with noise points in gray. To start, let's load our CSV. As we've seen, we have a mall customer CSV in the folder datasets. We'll load that in. We'll be using annual income and spending score so the geometry is visible in 2D. This raw scatter plot is just to see the scale at this point. Income spans a larger numeric range than score, so we'll standardize to make things fair. After scaling, both axes are comparable, which matters because HDBscan, like HDBscan, is distance-based. If we have poor scaling, our results will be off because then one feature will dominate over the other. A quick word on distance metrics because they define the neighborhood geometry that HDBscan can see. Euclidean distance is the default, which is straight line distance in a feature space. It's a particularly good choice for numeric features once you standardize them, because then each axis then contributes fairly. Manhattan, or L1 distance, measures block by block differences and can be a bit more robust when single features spike. Cosine distances care about direction rather than magnitude, and is a popular choice for embedding or very high dimensional text features. There you typically L2 normalize vectors instead of standardizing them. For geospatial data, you'd use pre-computed distant matrix. In this video, we'll just stick with Euclidean on standardized numeric features, because it keeps our story simple and matches the mall customers' examples well. Just know that swapping the metric changes the shape of the neighborhoods, and in turn, the clusters HDBscan discovers. For our demonstration, we'll keep min cluster size at 5, and we'll set min samples to none. We'll also stick with Euclidean distance. This is our result. The plot shows colored clusters in gray noise. You can see that we have a red cluster, a blue cluster, an orange cluster, a green cluster, and in the middle here, we have our biggest cluster, the purple cluster. You can also see the gray points to the sides, which HDBscan has labeled as noise, meaning that they don't confidently fit into any one of these clusters here. A higher noise rate isn't always bad. It often means cleaner clusters. But if everything becomes one blob, we can increase min cluster size or set min samples to a positive number like 10 or 15 to get more conservative boundaries. Let's take a look at the membership strength, or how confidently each point belongs to its assigned cluster. After fitting, HDBscan gives you a membership strength per sample in cluster dot probabilities. This is a 1D NumPy array which is aligned with our rows. Points near the heart of a cluster gets values close to 1. However, borderline points fade toward 0 and noise points are at 0. This is very useful if you need to filter out low confidence assignments or rank points by how representative they are. Our high confidence clusters are in the middle, designated by the bright yellow. But our noise points, you can see here, we have very low confidence that these points belong in this specific cluster, so these are labeled as noise. Let's take a look at HDBscan's condensed tree, which shows how clusters appear and persist as we move from low to high density. The vertical axis represents density. Lower on the plot means denser, while being higher on the plot means that it is less dense. Each vertical column is a candidate cluster. The farther it extends downward, the more stable that cluster is across many density levels. Thickness and color indicate size. Our thicker and warmer columns contain more points. Our short, thin branches near the top that die quickly are transient groupings that either merge into larger clusters or get treated as noise. In summary, we should look for tall, thick columns, and these are our reliable clusters. The tiny twigs that vanish quickly aren't. Now let's take a look at our HDBscan clusters and versus its membership strength. Comparing it side by side, we see our takeaway. The left is what HDBscan assigned, and the right is how sure it is. If you need super clean segments, we only keep only points above some membership threshold, like 0.7 or 0.8, and treat low confidence or -1 as noise. But if you need broader coverage, lower the threshold and accept a bit more fuzziness around the edges. In conclusion, HDBscan is a density-based clustering method that builds a hierarchy across many density levels and selects the most stable clusters, while also labeling uncertain points as noise. You can tune granularity with min cluster size and optionally min samples, so you don't have to guess a single EPS like its cousin DBscan. Thank you for watching, and I'll see you in the next video.